I'll just wait till the recording starts. Okay. So in the last class, we had discussed convex sets. A convex set is a set where if we take any 2 points and we connect these 2 points, then all points on this connecting line will lie within the set. Now, obviously, this is not a convex set because we can take points like these. So these points are outside the set. So this is a what we call a concave set. So a convex set is this. Okay. Now, convexity and concavity, as we have defined it, now we are going to extend the concept to functions. Okay. So if we, this is a function, and if we take any 2 points on the line and connect them, we will see that this is the function and this is the linear combination. Let's call this x1 and x2. So this is the linear combination of all points over here are linear combinations of x1 and x2. We say it is suppose x bar. Okay. So this is x1. So if we take a point like this, x bar, this is x bar. And over here we have x1. This is, sorry, it's not very well drawn, but you know. Okay. So this point is actually the linear combination of x1, function of x1, and oh, sorry, I'll just okay. So this point A can be written as this, and this point B we can say is okay. So if the function is convex, then sorry, if it is concave, then this relation will hold. Now, obviously, if it is strictly concave, then we have A is strictly less than B. Okay. So
So,
basically,
what did you write as B equals to F? What it's written?
okay,
Lambda.
sorry, this is lambda. So what we are taking is the linear combination of x1 and x2, which is x bar. Okay. So what is the functional value of x bar? This is equal to, by the way. Okay, so B is basically the functional value of x bar.
Okay.
So what we are saying is that if we draw the line connecting 2 points, then points on this line will lie below the curve. So if we draw a line between 2 points on the function, then the curve will be above the line. Okay, so this line, it is above. And if we are talking about convexity, it is obviously the opposite. So here, what we have done, no, I think I'll draw a fresh one. Okay. So a convex function is the so we take any 2 points, x1 and x2, and we connect them. Then any point over here, if we take a point x bar, this is below the line. So what we get is the curve or the function lies below the line. In this case, it is a strictly convex curve, but we can think of a, sorry, it's awful. Yeah. So this is weakly convex or simply convex. See, if we take a point like this and if we connect it, the line is above the curve. Okay. But if we take a point like this, then it is equal to the line. So that means the convexity definition should be modified slightly. It lies, instead of writing below, we should write it lies on or below. Okay. So the curve uh, lies on or below the line. Or we can reverse this. We can see that the line lies above or on the function. In this case, it is always above. In this case, it depends on the points that we are taking. Points like this and points like this, uh, it's going to be above. But if we take a point on this segment, it is going to be on the function. Okay. Similarly for concave, if you want to draw a strict concave, weak concave, it will be like this. So the technical definition is that, let us call this B and this is A. Okay. So A is given by and B is given by function of x bar when x bar is equal to when lambda is a fraction between sorry, lambda lies between 0 and 1. So here we can see that A will be greater than equal to B. This is for convexity, and for strong convexity, it will be satisfied as a strict inequality. Okay, is it clear or should I repeat it? Yeah. So is this clear or should I repeat it?
No, sir, it's clear.
Okay. By the way, have who has become CR?
We don't have
We
a
haven't
CR yet.
decided yet.
Okay. So you'll have to vote for it. Okay. So you can see the technical definition over here that function f is convex if fx, actually this is x is x bar, okay? Fx is less than equal to, so basically I'm saying that I'm taking this, x bar is the linear combination of x1 and x2. So this is the functional value. This will be less than if we take the functional value and we find out the linear combination. So lambda fx1 plus 1 minus lambda fx2. So we'll get a point like this. This is a point of the arc. So f bar is greater than f of x bar. And concavity is simply the opposite. Okay. Now let's define the level set. A level set of the function y is a set L such that fx is equal to c. So basically what we are seeing is that if I go back to the paint, let's see. Don't see. So we have the domain over here and we have different points over here. And for convenience, okay, sorry. So each of them maps onto a point over here. So if this is x1, let us say we get x y1. If it is x2, we get y2. Okay. Now y1 and y2 are different. For convenience, let us assume that we can arrange it in this manner. Okay. So the level set is those x's. Okay. All the x's over here such that the corresponding y is the same. Okay. So that means if we take, let us say x1, I get f1 over here. If I take x2, I get a slightly higher value. Okay. It's going up. Now I come into this set, level set. It is same. Y is the same. X4, Y is again the same. Then when I come to X5, it goes up. X6, it comes down. So this is the level set. So it is those values in the domain which will give me the same value of Y. Now, if you have a one-to-one function, what is the level set?
Many to one function.
No, if you have a one-to-one function, what is the level set?
Null set?
Null set.
It's a null set. Because for every x, we have a different y. So when can a level set exist? If you have a many to many, will it exist?
Yes.
Yes, sir.
Yes, sir.
Okay. Only many to many.
Many
Many
to
to
one.
one.
Many to one.
Many
Many
to
to
one.
one.
One to many.
No, sir.
No,
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 sir.
sir.
No, sir.
Okay. Now just tell me one thing. So that's your answer, right? One to many and many to many, right? Now tell me, how did you define function? What type of mapping?
One to one and
One
many
to one and many to one.
Many to one. So many to many is a mapping, but it cannot be a function. Uh, Now, what are examples? I mean, level sets are something that is very important to us. Uh, One example of a level set is the budget line of the consumer. Sorry. In the last class, we had said that M is the income of the consumer and he spends his income on two commodities, X1 and X2, with a price of P1 and P2. Suppose savings is 0. That means he's spending his entire income on X1 and X2. Right? In this case, we showed that we can write in this way. This is the expenditure, and expenditure has to be equal to income. Right? Expenditure cannot be greater than income. You don't have enough money. It can be less than income, but we are assuming savings are 0. Okay. And this can be represented by a straight line. Okay. Now, this is a level set because if P1 and P2 are fixed, right? If you take any points like this, right, and put this into the function, the functional value will always be m. Okay. Let's think of an example. Okay. Now, can you identify some members in this level set? What are the combinations of x1 and x2 which will give me exactly 100?
So 25 and 10.
20 to 30.
25 is 50. Yes. 25 and 10. Another?
So 30 and 8.
30 and 8. Yes.
0 and 20.
0 and 20. If you go to the
5
other,
and 18. 5 and 18.
15 and 6. 15 and 6.
15 and 6. If you go to the other extreme of this,
50 and 0.
50, 0.
okay. So in this way, all these points, these combinations, okay, the combinations of x1 and x2, which lie on this line, okay, we can find out by solving this equation. All this will give me a level set. Now, in case of consumer theory, we can also think of another type of level set. One level set, as we have seen, is what we call the budget constraint. Now, why does a person consume the commodity X1 and X2? We assume that consuming X1 and X2 gives the person some satisfaction. Okay. Now, this satisfaction is called utility. So we can think of a utility function X1 and X2 such that if you consume more of X1 or more of X2, then your utility will increase. Okay. And similarly, if X decreases, your utility will also decrease. Okay. Now think of this point A. Right. Now suppose we take a point like this, B. What is happening to consumption of X1? Is it increasing?
Increase.
Yes, sir.
X2?
It is also increasing.
Okay. So what will happen to utility?
It will
It
increase.
will also
Increase.
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 Okay. So UA is less than UB. If we take a point like this,
Utility
So then
will
it will decrease.
It will decrease.
okay, so we can write this. Now, if we take a point like this, what is happening is, in case of D, X1 has gone up, so utility increases, right? But what has happened to X2?
It's gone down.
What will happen to utility?
It will decrease.
It will decrease. Now, we can fine tune the increase and decrease in such a way that this increase and the decrease are equal. They cancel out. If we can identify this point, then what is the relation between UA and UD?
Sir,
It will
indifferent.
be equal to.
They
indifferent.
are, they are equal. So we can take another point like this, E, and here also we can fine tune. Here, in this case, the opposite happened. X1 decreases, X2 increases, and we can choose them such that utility is the same. Okay. So that means utility of A right? Therefore, XA, XC, and XD, these all belong to the level set. Okay. So if we substitute, if we use the vector X, XA, or the vector XC, or the vector XD, we will always get the same utility. And if we connect them, we get, as you have said, we will get the indifference curve. Okay. So in consumer theory, we have two types of level sets. One is the budget constraint, the other is the indifference curves. In case of the producer, in case of production theory, the equivalent of the budget line is the ISO cost line. This is the total cost, and we assume that there are two inputs, labor and capital, and these are the prices of labor and capital. So again, this can be this will be a straight line, right? And all the combinations of L and K, which lies on this ISO cost, all these represent the level set. So all combinations of L and K such that C equal to WL plus RK, bar means it's constant, is a level set. And equal to the, yes,
So, sir,
yes,
these are one-to-one functions, right? Uh, the
no,
budget.
it cannot
Yes.
be a one-to-one function.
But, sir, isn't the budget line and the indifference curve one-to-one functions?
No, see, if you're talking about a level set, what you basically mean is that a particular X is generating Y, that is X1, but X2 is generating Y, right? If The concept of a level set means that y1 and y2 are equal. So what does it imply? x1, x2 implies this.
Okay, I get it. Yeah.
So it has to be a many to one. Only a many to one mapping can generate a level set. Okay.
So, sir, what kind of mappings are the indifference curves on the budget line?
Okay. So in that case, uh, see, this is x. So now we are talking about vector. We have points like x1. These are capital, right? And each of the points indicate a particular value of x1 and x2. Okay. So each point on this domain represents a combination of x1 and x2, the two commodities that you are purchasing. If this is the budget set, for instance, both of them are generating the same income or expenditure. This generates a different income level. So for instance, if you consume x1 and x2, your expenditure will be 100. But if you consume x3, a different vector, your expenditure will be 110. Okay, so in the example that we had shown, it was 2x1 plus 5x2. So a point like, let us say 25 and 10 will give me an expenditure of 100.
Yes, sir.
If I have, let us say, 3012, this will also give me 100. But suppose I go for 3010. It's how much? 60, 110.
Yes, sir.
Or if I go, let us say, for 20 and 10, it will be 90.
90.
So these are not part of the level set, but these are part of the
Okay.
level set.
Okay, I get it now.
Okay. And
Okay, sir,
similarly,
thank you.
if you go for the indifference curve, what I'm saying, instead of B, it will be utility. So you have a utility level over here. These two combinations will give me a utility of 10, 100. But this will give me a utility of 110, which is different. Okay, this similar to a consumer, we have the isocost line and we also have isoquants. So along the isoquant, so this is a combination, production is equal to, let us say, Q1, 0. Here production is equal to Q1, here production is equal to Q2. Okay. So all these points, all these combinations of labor and capital creates one level set. This is another level set where output level is higher. And this is a third level set. So is this clear?
Yes, sir.
Yes, sir.
Yes, sir.
So basically what I'm saying is that the domain may comprise of several level sets. Each of them corresponds to a different value of y. Okay. Now, if you think about this in the earlier case, I can't draw the y-axis. It's always slanted. Okay. So suppose I'm drawing a budget line. Right? So all points over here represents a level set. Okay. Now, suppose the consumer gets his income goes up. So income becomes, instead of 100, it becomes 120. So this will be his budget line. Right? Now, how do we represent this budget line? Obviously, the slope is same, so it will be parallel to the original budget line. But will it be on the budget line, over here, or over here? Where will it lie?
It will shift rightward.
So upward.
It will
Yep.
shift upwards. Okay. This is called the better. You will be better off if you can come to this level set, right? Similarly, if you think about the indifference curve, right? Look at this point and this point. Which is better? B is
B is
better?
better.
B is better.
B.
B is better.
Yeah. So we can write like this. So again, we have got two level sets, one corresponding to U1, the other corresponding to U2. But U2 is better than U1. So using this, we can define the concept of a better set. So a better set is that if you take the uh, vector, see the functional value uh, will be better. How can I draw this? Can I draw over here? No, I can't draw. Okay, can you see the mouse?
Yes, sir.
Yes, sir.
Okay.
Yes.
So we have let us say that this is the level set. Okay. And we are taking a point x0. Okay. So a better set is those points which will give me a higher functional value. So if I take a point like this, okay, this is the different combinations of x1 and x2. The functional value y, in this case it is income or expenditure, is higher than the value over here. Is it clear or shall I repeat it?
It's clear, sir.
It's clear, sir.
So in this case, we can see this is the budget line. As we move to higher and higher budget lines, it represents a better set. So if we start with C0, all points C1, C2, C3, all these are in the better set. If we take C1, then C2 and C3 are in the better set. Similarly, we can also define better set for indifference curves and isoquants. Now we come to the concept of quasi-concavity. we see that a function is quasi-concave if for every point in X, the better set B, right? So this is the function. There's a function which generates all these indifference curves. There's a function which generates these budget lines. So every point, we take a point and we find out the beta set, right? This beta set is convex. So if the beta set is convex, then the function y, which has generated these cost functions, this is said to be quasi-concave. Over here,
So
yeah.
only one of the better sets have to be convex
No,
for.
no, this entire portion.
Okay, okay.
So that means if I take C1, it will start from here.
Yeah, all of them. Okay.
Not only all of them, there are also lines over here. So these points are also in the beta set.
Okay.
So in this case, if I take C2, what is the beta set? The beta set is the shaded line, shaded area. See, if you take any 2 points over here, it will be convex. See, these parts are also green. Okay. This is also a point on the beta set. So if I take a point over here and a point over here and connect them, it will lie within the beta set. So this is a convex set. This is, in fact, a strictly convex set. This is a weakly convex set. Okay. Since the beta set is convex, we say the function is quasi-concave. Now look at this. What is the beta set of this? Points over here or points over here?
In upper direction.
Upper direction. Okay. So is this beta set convex?
No, sir.
Just a minute. So all this is the convex set. If I take a point like this and a point like this, so all these are lying outside the beta set. So it is not convex. B is not convex. Therefore, the function which is generated this curve is not quasi-concave. Okay. But if you look at these curves, what is the beta set? Points like this. See, if I connect them, if I take a point like this, if I take a point like this, all these points are in the beta set. So that means it is the beta set is convex and this function f is sorry. So no, this is convex and this is quasi-concave. Okay. Now when I typed it, I forgot to type some parts. So can you help me out? We are trying to define a verse set.
That yields a value that is at least less than that of
Less than
a
equal.
functional value.
It is at least less than
Less.
or equal to. Thank you. And over here.
So at least a small.
So we are, okay. Okay, just give me a moment, please. Yeah, sorry. Okay. Therefore, yeah. How have I defined convexity?
The worst set.
What set?
Is a concave set.
The concave set.
Is the concave set. It is
If
strictly convex.
W is strictly concave.
Strictly concave.
Okay, very good. Okay, so we've finished with functions, and I'll just discuss something of sequences. Not much, but I'll leave theorem for the next class, and then I'll go to some applications. Okay. Now, what is a sequence? A sequence is you can say it's a series, roughly. You have a numbers which follow one after another. So they can generate, it can be generated by functions like y equal to n square, y equal to log x, y equal to 1 by n, something like that. So for instance, this y equal to n square generates 1, 4, 9, 16, like this. Now look at this sequence. 1, half, 1 by 3. What is this? Is basically 1 by n. So what is the difference between this and this? Both of them are sequences.
So could you repeat?
What is happening in this series? What is happening to y? In both cases, x is
They're
going up.
approaching 0.
Sorry?
In both the sequences, the value of y is approaching 0.
In both the sequences. So
Sir, one is increasing and one is decreasing.
One is, yeah.
the first one is increasing and the second is decreasing. Now look at this. This is also a case when is this decreasing? Is actually increasing. But again, it is approaching 0.
Yes, sir.
So the difference is basically if we take the number line and 0, in the first case, we are moving like this. In the second case, we are moving like this. But in both cases, the sequences are approaching 0. But will it be 0? When will 1 by n be 0?
When n is infinity.
But it's infinity is just a concept, right? We can't use it for mathematical operations. So that means what is happening is that in both cases, the series is asymptotically approaching zero. Okay. They will never actually be zero. They will become closer and closer to zero. Have you, any of you read Concavity? Pin drop silence. So no one's read it. You should read it because it's কি বলছো? You should read the book. Those of you, some of you are non-Bengalis. You won't be able to read it. I don't think it has a translation, but it was written about I don't know, about 150 years ago. But what I like about it is it's a very fantastic portrayal of India. Not 150 years ago. It's a portrayal of India now in 2020. So the story is about a girl, Concavity, who is supposed to be, her parents receives a marriage proposal, and suddenly the people, the villagers spread a rumor that the boy whom she's supposed to marry is actually a gambler, a drunkard, and the marriage is broken off. So Concavity falls seriously ill, and she has a dream. And the entire story is about the dream. So, and one story, she is lost in a jungle, and she meets a foreign frog, Kola Bang, Saheb Bang. So, since she's lost, she asks the frog that how do I get out of the forest? So initially the frog is very arrogant. He tries to speak to her in English, saying he had fed dam. But actually the frog is very kind-hearted, and he agrees to help her, provided that she helps him out in return. So apparently the fox has borrowed a rupee from him. And the terms of repayment was that every day he will repay half of what he owes. Okay.
Sir,
So
who
what
is
does
the
it mean?
writer?
Troilokonath Mukhopadhyay.
Okay.
What happens is he asks on the first day, how much does a fox repay? The loan is 1 rupee. So how much does he repay?
Half a rupee.
50 paisa. Next day?
50 paisa.
50
No.
paisa.
Half of what he owes.
25 paise.
25.
25 paisa, yeah.
Third day?
12.5 paisa.
Okay. Fourth?
6.25.
6.25.
So what happens? Does he ever repay the 1 rupee?
No.
No, sir.
No, sir.
Yeah. So the frog solves this problem, and he gets very upset and he starts crying. And he says, you have heard the word Banger Adhuli. So he says that, hi, ki holo, amar Banger Adhuli chole gela. Banger Adhuli means something which is very prized and which gets lost. So Anyway, this part is not very important, except it's a caricature of people who are trying to imitate foreign customs. But what it indicates is this asymptotic series. You're always approaching zero. See, ideally, a time should come when the loan amount should be zero. But what happens is you're always going down. That loan amount is decreasing, is becoming very small, but it never becomes zero. So this is a case like this: 2, 4, 6, 8. You're always decreasing. It does not have this is increasing. So you never have a limit. This is the opposite of the earlier sequence. In these cases, the sequences approach zero, though they never actually equal to zero. So they have a limit which is zero. In this case, the series just goes on increasing. It does not have a limit. So series which do not have a limit are called divergent. Series which have a limit is called convergent. So you can think of it in this way. So suppose you have a value in, see, the series is converging to n. It is decreasing, but it is converging to n. Here also you'll see it is converging to n. But if you think of a sorry, I'll try it. In this case, this is divergent. This is also divergent. Okay, it's moving continuously away from n. Here also you are continuously moving away from n. But in these two cases, you are approaching n. Although you never touch n, you're still coming closer and closer to n. Okay. Now, if you have a convergent series, then n is the value towards which the series approaches. We call this finite value n as the limit of this sequence. So technically, we can say that a sequence is said to have a limit L if we take some value epsilon, which is very small and positive. So there's some value n such that an minus L will be less than epsilon whenever n is greater than n. Okay. So basically what we are saying is, I think it'll be easier if I draw it. So we take a point an. Let us say this is a1. Remember, epsilon is positive. So a1 minus n is always, in this case, it is positive. In this case, if you take the absolute value, this is not zero. Basically, that's what we are trying to see. If you take a1 minus n, right? if A1 becomes N, then what will this be equal to? Right? What we are saying is A1 will never become N. How can we ensure that? That the gap between A1 and N, that is never equal to 0. If you're coming from here, see, there's a gap over here, gap like this. See, if you're coming from here, there's a gap like this. So suppose the series is decreasing. As we are coming down, A1, A2, A3, right? We will come to N, but there will always be a small gap. On the other hand, if we take an increasing series, A1, A2, and so on, we are increasing this, the gap is getting reduced. A1 minus N, that is falling, but it will never become 0. It will always be equal to some value epsilon. Okay. So limit is some value which you will never touch, but you're always going to approach. So technically we write limit n tends to infinity, the sequence will become L. It approaches L. Is it clear?
Yes, sir.
Yes, sir.
See, it's always a few students who are saying, yes, sir, yes, sir. But I mean, if the others feel that if you have any problem, do let me know. Okay. Now, next we're talking about bounds. Oh, there's a typo over here. Let me correct this. Okay. So in case of an upper bound, K, let us say K is the upper bound, and this K is the lower bound. Okay. So again, what's happening is K is the upper bound means that when AN is increasing, it will always be less than KU. On the other hand, the smallest value of AN will be greater than KL. Can you tell me, are these sets open or closed?
They are open.
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 What will happen if it's closed?
It will become
Less than
equal.
equals to KU and
Less
equal
than
to
equal
KL.
greater than equal to.
Equal to.
K value will be exact upper and lower bounds.
Yeah, you'll have exact upper and lower bounds. And an unbounded sequence is when you neither have an upper bound or you don't have a lower bound. So again, it's possible to have 4 types of sequences. One is bounded from both top and below, upper bound and lower bound. You can have unbounded. There are no bounds on either stretch. And you can have a mixture. You have an upper bound, but no lower bound, and opposite. Next, we are referring to monotone. Monotone means the sequence is either increasing or it is decreasing. If it is strictly increasing, that means A1 will be less than A2, which will be less than A3. Decreasing means just the opposite. A1 will be maximum, is followed by A2, A3, and so on. And if it's strict increase, then instead of the sorry, it's wrong. So increasing means it will be no, just a minute. Sorry. This is okay. Yeah. Strictly increasing means it's satisfied as a strong inequality, and just increasing means it's satisfied as greater than equal to. Okay. This diagram will make it clear. Is this an increasing function or decreasing function?
So can you take out the previous slide once more?
Yeah.
Thank you, sir.
Is this increasing or decreasing?
So it is
Increasing.
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 It's increasing.
So, but a
But-
monotonic function has to be either increasing or decreasing throughout, right?
It's both
Yeah.
increasing.
But if you look at this part, okay, it's more or less, let me say this is, yeah. If you look at this part, what is happening? Is it increasing over here?
No, sir.
No,
it's
sir.
No, sir.
Stable.
both increasing.
It's not decreasing, it's constant. The value is remaining same.
Okay.
So if I call this A1 and I call this A2, what is the relation?
Level. Level.
It is equal to.
Equal.
Yeah.
A1 is equal to. Okay. So you have some nodes over here. Let's call this A1 and this A2. This is A3, A4, A5, so on. So A2 and A1 increasing. A2 is greater. A3 is greater than A2. A4 is greater than A3. This is again greater, but here it's equal. So it's it's monotonically increasing. If you look over here, what happens?
So it is
This is
strictly
also
increasing.
monotonically increasing. It's strictly increasing. Yeah. Over here,
Decreasing.
It is simply decreasing.
decreasing, but it's
Not strictly.
yeah. And over here,
Strictly decreasing.
It is strictly
Strictly decreasing.
and this,
So can't be said.
this is not a monotone. Okay. Okay. So this is a theorem which I'll discuss in the next class. But now let's return to the elasticity part, and I'll try to show you a theorem. So this theorem basically looks at the relation between the elasticity of demand and expenditure. Okay. So what is expenditure? How do you define it? For a one
Price
commodity case,
P into-
price into X. Okay. Now we want to see what happens to expenditure when price goes up. What do you think will happen?
If X remains same, then the expenditure will also rise.
Remember that if you draw the demand curve, this is negatively sloped.
Okay.
That
Yeah.
is the law of demand. Okay. So when price goes up,
X should go down.
this is positive. This is negative. right? So what will happen to expenditure? We can't say offhand, right? For instance, suppose your price was 5 and demand was 10. So expenditure is 50. Now suppose price goes up to 6, demand falls, it falls to 8. Expenditure is 48. That is one scenario. So your expenditure has decreased. But suppose demand fell, but instead of 8, it fell to only 9. What happens to expenditure in this case?
Increases.
Increases, yeah.
It has gone up. Okay. So if I give you the price and quantity, the original price quantity and the new price and quantity, you can tell me that whether expenditure has gone up or not. But can we generalize this? One way of generalizing this is, sorry, this will be right. So what does it indicate? It indicates basically what is happening to expenditure when price goes up. Yeah. So this is just U into V. So how do I write it? You know the chain rule? U into V. If you want to differentiate this,
Yes, sir. DDU plus DDV divided by U plus V.
no, it will be
U
U into dV.
dV plus
Ha ha ha.
into
Yeah.
du over uv.
Yeah. Okay. So in this case, how do I write it?
P dx dp plus x
plus x.
P
pdx
just
dp plus
plus
x.
x. Yes.
dP cancels out. Okay. Acha. Now let us take x common. So I have to bring an x over here. Right? And for convenience, I just bring this forward. Does this look familiar?
Elasticity
So mod
of
value of
demand.
elasticity.
Right? I can write it in this way.
yes sir.
And remember that elasticity can be greater than 1, equal to 1, less than 1. Okay, so if elasticity is greater than 1, what do we have? This is greater than 1. So x is always
Total
positive. The bracket will be negative. So what does this mean?
total
D
If
expenditure
price
is
rises, then
inversely
total
related with
expenditure will
price.
decrease.
be negative. Yes. Elasticity equal to 1.
So the total expenditure will not change.
Yes,
Is
total
directly
expenditure.
yes, it does not change with price.
Yeah.
Yeah, this is 0. Yeah. So remember that we said that elasticity equal to 1
Hyperbola.
is a rectangular hyperbola. Yeah. What does it indicate?
Equal area.
Hyperbola is that if you take any point,
Constant.
the area
Constant,
is
yeah.
same. And what is area? Yeah. What is area? See, this is
P
the
into
price,
Q.
and this
P
is
into
what?
Q, yeah.
P into Q.
Yeah.
Q1 Q1 equal to P to Q or
So
equal.
expenditure. So expenditure is always constant. That is why d by dp equal to 0. And this is obviously right. Think of this intuitively. Just look at this and this. Is it intuitively obvious that you should have got positive over here? What is elasticity? Suppose the price, as you can see over here, price change is same in both cases. It's gone up from 5 to 6. What has happened? In both cases, demand has fallen. Okay. What does elasticity mean? When price changes,
Responsive.
demand will change a lot. That is the meaning of highly elastic demand. What is the meaning of inelastic? When price changes, when price goes up, demand will change,
Doesn't
Does not
change
change much.
very slightly.
very slight.
Yeah.
Will not change significantly.
So look over here. What is the demand curve in this case? It has fallen from 10 to 8. And here it has fallen to from 10 to 9. Which is more elastic?
When it fell to
Eight.
So the
First
first
This
one.
one?
or the
First one.
fourth case.
The first one?
10 to
Yeah.
8.
8.
Hmm.
So it's more elastic when expenditure falls with rise in price.
Yeah. So that means basically what is happening is your del P is positive, right? Now, what is happening to del X? Elastic demand curve means this is a high value. Therefore, expenditure is going to come down. Inelastic means that del X is going to be very small. So that means this effect, positive effect, will dominate. Okay. So if you have an elastic demand curve, the consumers will react sharply, significantly to a price change. Therefore, expenditure, if price goes up, expenditure will come down. On the other hand, if you have an inelastic demand curve, consumers change, they react, but not much. It's a static situation. So when price goes up, the demand changes very slightly. So expenditure will go up. In this case, demand has fallen, but only by 1 unit. That is why expenditure has gone up. Okay. So is this clear? This is again a theorem which is going to be very useful later on. Is this part clear?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Okay. Now, I think you have discussed Marshallian functions and Walrasian functions, demand functions in the
Yes.
last class.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So what is a Marshallian function?
So the Q should be in the horizontal axis and P in the vertical axis. So like we just see the change in uh, P
See,
with
we always, wait a minute, we always draw like this. We always draw the
So
demand
the
curve
change
like
in
this.
we see the change in P with respect to changes in Q. Q is the deciding factor in Marshallian.
Okay, so what you're saying is this. Price
Yes.
is a function of quantity. In case of a Walra, quantity is demand is a function of price.
Price.
So the quantity demanded is a function of price, and here we say that the demand price is a function of quantity. So basically what we are saying is, suppose this is the demand. What is the maximum price that you are going to pay in order to purchase this amount? Marshall looks at it in this way. So you want to buy 4 units. What is the maximum price per unit that you're going to pay? Will you? So suppose this is P1. So if you want to buy 4 units, you're going to pay P1 for each unit. You will not pay offer more than P1. Walra looks at it in this way. You come to me and I say that, look, this is the price. And you say, okay, fine. In that case, this is the maximum amount that I'm going to buy. Do you get this? Here, the movement is like this. Here, the movement is like this. Now, in the earlier case, when I differentiated, did we have a Marshallian demand function or a Walrasian demand function? What type of demand function did we take?
Marshallian.
What are we? Okay. How did we do this? Right? Look at it carefully. Do you want to change your answer?
Walrasian, sir.
Yes, that's
I see
Walrasian.
the
So
Walrasian.
price moves first, that is I want.
Price.
So
Yeah.
graphically we do Marshallian, and in normal
No.
terms we do
No. It's not graphically. We always do it like that. I had told you about this, but I don't think you had kept it in mind. It's a minor point. The graphical representation is always price over here, quantity over here, whether we take Walrasian or Marshallian. Okay. I mean, when you go for stability analysis, you will see that price is always on the y-axis, even if it is a Walrasian. Theoretically, what you're saying is perfectly correct. If I'm taking Marshallian, then this is correct. In case of Walrasian, it should be quantity as a function of price. The explanatory variable should always be on the x-axis, and this should always be the dependent variable. Right? But convention is that we always use price over here, quantity over here. As I told you, the difference is only in the causation. The causation is from the quantity. We are moving like this. Here, we are moving like this. Okay. But in both cases, the quantity division, the y and x axis, are same. Y is always price, Q is always the horizontal axis. I mean, if you ask the what's the logic, there's no logic. It's just convenience. Now just suppose if you take this instead of dp, what will happen?
So P.
Okay.
So P plus Q dp dq.
I want to write this out in elasticity terms. So what do I do next?
So we take
take
P
P as
common.
common.
Take P common.
Sorry, I made a mistake over here. This will be Q. Next.
So 1 P
So
equal
1
to
plus
1.
1 by E.
1 plus 1 by E.
1 by E.
Yeah. And don't forget the minus. So it's 1 by E. Okay, so just be a bit careful. Normally, if you differentiate by P, we are going to get this relation. But if you differentiate by quantity, you're going to get this relation. Now, in the last class, I had defined three concepts. Total revenue, which is price into quantity. We have got average revenue, which is TR by Q, which will be price. In fact, this is often referred to as the demand function. And we have the marginal revenue, which is equal to tell me what is this?
So P
P
plus
plus Q into dp
Q
dq.
dp dq.
You've just derived this. It is right?
Yes, sir.
Yes, sir.
Yes, sir.
Or
Yes,
we
sir.
can write this as
Yes, sir.
right? MR equal to this.
Yeah.
Yes, sir.
Now, suppose we have a linear demand function. Okay. Remember, I told you what is so special about the midpoint?
Elasticity is
Elasticity
equal to 1.
Elasticity is
One.
divided into its highest.
Unit elasticity.
Okay. So at this point, elasticity is equal to 1. What will be marginal revenue over here?
0.
It will be 0.
0.
0. Yeah.
So MR is okay. At this point, what is elasticity?
Greater than 1.
Greater than 1.
Greater than 1.
If it is greater than 1, this will be less than 1. So MR will be
Positive.
Positive.
positive but less than AR.
Less than AR.
AR.
Okay. And in this range,
MR will be negative.
Negative.
MR will be negative. Okay. So you'll see later on that when the producer tries to find out what output to produce, he will always be in this part. Can you say why? Why doesn't he go over here? If he's increase, see MR, the meaning is, what does MR
Total
mean?
revenue is decreasing after that
Yeah.
point.
MR is the change in total revenue when you're selling more. Okay. So what is happening when you're selling more, the total revenue is actually coming down. That is why there's no point in producing or selling beyond this point. So this is the maximum point.
Total revenue
Which will
is
be selling.
maximum. Yeah. Okay.
Yeah, I've not come to maximum now. That will
So
be
can
the
you repeat this once more?
this part. See,
Yes, so why the seller sticks to only that region?
okay. The marginal revenue is that if your quantity changes, how much does total revenue change? This is from the definition of marginal revenue. Okay. Now suppose Q increases, right? MR positive means that total revenue goes up. MR equal to 0 mean total revenue is the same. And MR negative means your total revenue decreases. Right? So over here, what is happening? If you sell more, you earn less. So will you sell at this point?
No,
No.
sir.
No.
No, sir.
Yeah. So that means a producer will never come over here. This is not feasible for him. So he will be either on, he will generally be over here. Elasticity will be, he will be in this range. Okay. So I'll end at this point. If you have any questions, you can ask. Okay then. If there are no questions, I'll.
Sir, I have a question from previous day class. Sir, in the
Yes,
exercise question 5, the question asked about find the output levels at which the firm just breaks down. So my answer is coming in complex number. Is it possible?
Yes,
wait
sir.
a minute.
Yes, sir, exactly.
Which page was it?
Sir,
In
Page
voice
57.
Page
57.
57.
59.
Over what range of price does the firm make a loss at all output levels? That was the question.
Sir, in first paragraph, there is another question.
Oh,
Find the output levels at which the firm just breaks down even.
okay.
Yes,
So over
sir.
there. I haven't discussed costs so far. Let me see. Where's my pen gone? Okay. So just like in revenue, we can also think of total cost, average cost, and marginal cost. Okay. Total cost you can understand. Average cost is simply total cost by quantity, and this is total cost by Q. We write total cost often by just by C. Okay. Okay. So the average cost is x0 minus 20x plus 120. Okay. The output price is 10. Okay. So you have to find what is called the break-even point. Okay. Break-even is your profit is equal to 0. Now, what is profit? Your income, which is total revenue, minus cost.
Total cost.
Yeah. So this is 10 into, I've written it Q, so I'll just maintain this. X square plus 20. Sorry. So this has to be equal to 0. Okay, so minus Q square. This is 30Q minus 120 equal to 0. Q square minus 30Q plus. Okay.
Sir, it is given that Y is average cost in dollars per unit of output. So Y into Q.
Oh, sorry. This
Yeah,
is,
he did so.
sorry, this will be Q3. This will be Q square. This will be 10.
Or sir, can we take just like AC equals to price?
Yeah. If you divide by quantity, it comes to the same thing.
Yeah.
Okay. So in that case, you're going to get this equation, right? I mean, if you divide by quantity, no, this will come into the 120 part.
Yes, sir. It was 110.
Yeah.
It was 110.
So the equation is x square minus 20, 110. Okay, so minus b plus minus b square is 400 minus 4ac. Yeah, it's becoming complex.
Yes, sir.
So if you're getting this part, that's the answer. I mean, theoretically, what you should have got, this should have been lower. And
But sir, how to sketch the graph?
no, don't try there. There's a typo over here. Think of it as if it was something, if it was lower, let's say if it was suppose 160, then you could have solved it. It would have been minus 20 plus minus 240 by 2. You could have solved it. So don't worry about this solution. Okay. Second is sketch the average cost function and show the solution. Okay.
Sir, I have a question.
Yes.
Instead of cancelling the x out, can't we take x as common and then show x is equal to 0?
See, x equal to 0. Yeah, what you're saying is true. In this case, it is true, but is it a very interesting solution?
No, sir.
I mean, right now your break-even profit is 0. None of you are producers.
So we are getting complex numbers. So 0 is better than getting a
Yeah,
complex
it's
number.
better. Yeah, you're definitely correct. But normally we try to look for a positive Q. The producer is producing something. I mean, he can obtain this production level. That is one reason, and there's another reason why Q equal to 0 can create a problem. But okay, now what's the sketch? The average cost function, x square minus 20x. So over here you can just put in values. So let us say this will be 1 minus 20 plus 120. So this is 99. If I put in 2, this will be 4, 4 and 20, 80 plus 120. So it will be 44. If I put in 3, 9, this will be 6.
So the first coordinate will be 101.
Yeah, sorry, it's 101. This is also wrong, isn't it? 2 means 40. So 40 means this is 80. It will be 84. 960. So it will be 69. But you can see that it's decreasing, but the amount of decrease is gradually coming down. So it will be like this. And your price is constant at 10. So ideally, your price is 10. In this case, this is the break-even point. Okay. Which is the profit-making zone?
Above 10.
Above 10. Okay. What is the, let us take this point. What is this rectangle? This is quantity. And what is this? Remember, this is the average cost function.
Yes, yes, it will be below.
So it's total cost, and this is total revenue. So beyond this, over this, the initial part, this is a loss-making zone. Here, you're breaking even. And here you have a profit.
So can I explain the second graph?
This one.
Yeah.
See, okay. See, this is the price, right? Price equal to 10. So if I take any point over here, suppose I'm supplying this, Q1, Q2. What are these rectangles? Price into Q is total
Total
revenue.
revenue.
Total revenue.
Yeah.
Total revenue.
On the other hand, if I take not the average cost, then any point over here, this is average
Total
cost.
cost.
So the rectangle is total cost. It's obvious. Okay. Now let's merge the graphs. Okay, over here, if you take if I produce over here, what am I getting? Total cost is greater than total revenue, right? So profit will be negative. So this is the loss-making zone. Over here, total revenue is greater than total cost. So this is the profit-making zone, right? And over here, you can see total revenue is equal to total cost, which we called the break-even point. So actually, the cost function that Hoy has given is wrong. But if you draw a conceptually like this, we can have several possibilities. Okay, what happens over here? Over here, what is profit?
Profit is 0.
No, in this zone.
It
This
is
is the
negative.
break-even point, right?
It's positive.
Here,
It
profit is
negative.
positive.
So negative.
It's
It's
negative.
negative. It's a loss-making region.
Yeah, here,
It is positive.
Profit is
Also
positive.
why?
So again negative.
What
It
is
also
total
negative.
cost? Total cost is this rectangle, right? And what is total revenue? This rectangle. Which is larger, total cost or total profit?
Total
Total,
cost.
total cost.
Total
It's
cost.
again a loss making
So it will
region.
be negative.
Yeah, so it's like this. This is loss, and this is break even.
Break even.
So if the producer enters the market, he has to produce over here. He will not get anything, but he doesn't lose out. It's the same as before. Here,
Shut. Completely lost.
there's no point in entering the market.
Inevitable.
There's no break-even point also.
Yeah. This is profit.
Profit.
All throughout profit.
Yeah.
So here,
The portion which is below that line will be profit.
Yeah, it's profit.
Yeah.
Yeah.
which is the break-even point?
The
There
2
are two
points.
break-even
Break
points.
even
Yeah,
point.
So there are 2 points.
we have two break-even points. Yeah. So these are the losses. He will choose a point over here. Okay. I'm sorry that Hoy tricked you. Okay, then we'll meet tomorrow.
Sir, attendance?
Attendance. It's okay. I'll give you attendance.
Okay, sir.
Thank you, sir.
Okay, so
Okay.
thanks.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.
Thank you, sir.